Night falls over Earth. From a distance, a gleaming star-like object streaks across the sky. The International Space Station, a symbol of human ingenuity and international cooperation. At nearly 28,000 kilometers per hour, the ISS orbits our planet approximately every 90 minutes, circling in a path carefully chosen to optimize science and safety. Yet, beyond the gleaming solar panels and bustling laboratories lies an invisible realm, a dynamic magnetic environment shaped by Earth's molten core and the tempestuous solar wind. In this cosmic dance, the ISS moves silently through Earth's magnetic field, a complex, shifting shield protecting all life below. This orbital whisper is a story of science and survival, an intimate dance between humanity's creation and the forces of nature that shape our existence. Earth's magnetic field is often visualized as a simple dipole, a giant bar magnet embedded within the planet. But this analogy is only a starting point. The field originates deep within Earth's outer core, where molten iron and nickel swirl in convective motions. This geodynamo generates electric currents that produce magnetic fields. These fields extend outward, forming the magnetosphere, a vast, comet-shaped bubble protecting Earth from the sun's charged particles. Within this protective shield are complex regions like the Van Allen belts, donut-shaped zones trapping high-energy particles. The magnetic field is vital. Without it, solar wind particles would strip away the atmosphere and bombard the surface with lethal radiation. The ISS orbits within the lower reaches of the magnetosphere, in a region where the magnetic field is strong but not uniform. Its 51.6-degree inclination means it traverses diverse magnetic latitudes, from equatorial zones to higher latitudes near the poles. This orbit passes through regions of magnetic variability. One of the most notable is the South Atlantic Anomaly, SAA, where the field is weaker and radiation levels increase. During SAA passages, astronauts and equipment experience heightened exposure to energetic particles, necessitating special protocols. The ISS acts as both a space laboratory and a sentinel, collecting data about this invisible environment. As a massive metal structure moving rapidly through Earth's magnetic field, the ISS experiences electromagnetic effects. Changing magnetic flux induces electric currents in conductive materials, a phenomenon described by Faraday's law of induction. While engineers design systems to manage these currents, they can still cause subtle interference or require careful electrical grounding. Charged particles trapped in the magnetosphere can penetrate spacecraft shielding, causing single-event upsets, sudden malfunctions in electronics due to particle strikes. Understanding and mitigating these effects is crucial for the station's continuous operation. Earth's magnetic field does not exist in isolation. It is constantly bombarded by the solar wind, a stream of plasma, mostly protons and electrons, flowing outward from the sun. The solar wind compresses the sunward side of the magnetosphere and stretches the night side into a long tail. During solar storms, bursts of increased solar activity, the influx of charged particles intensifies, energizing the magnetosphere and triggering geomagnetic storms. These storms can cause spectacular auroras, but also disrupt satellite communications and increase radiation risks on board the ISS. Mission Control closely monitors space weather forecasts to adjust ISS operations accordingly. To understand Earth's magnetic environment, the ISS carries several instruments. Magnetometers measure the strength and direction of magnetic fields around the station. Particle detectors track energetic particles, helping scientists map radiation flux. Plasma analyzers study the charged particles of the solar wind and magnetosphere. These instruments collect continuous data, improving our models of the magnetosphere's complex behavior. This knowledge aids not only ISS operations, but also broader scientific research on space, weather, and planetary magnetic fields. Astronauts aboard the ISS live within this invisible magnetic embrace, exposed to radiation levels higher than on Earth's surface. Although Earth's magnetosphere offers protection, it is partial and variable. Radiation exposure accumulates over time, increasing risks of cancer and other health effects. Crew members wear dosimeters to monitor cumulative radiation doses. When passing through higher radiation zones like the SAA, astronauts may limit activities or seek shelter in better shielded areas. Research aboard the ISS explores how radiation and magnetic fields impact human physiology, from DNA damage to neurocognitive effects. These studies are vital for planning longer missions beyond Earth's magnetic shield. Earth's magnetic field is not static. It fluctuates over multiple timescales. The magnetic poles wander, sometimes rapidly. Over thousands of years, the field weakens and reverses polarity. North becomes south and vice versa. These changes affect the size and shape of the magnetosphere, altering radiation environments. For spacecraft like the ISS, this means the radiation landscape evolves, requiring ongoing monitoring and adaptation. Understanding these dynamics is key for future crewed missions in low Earth orbit and beyond. The experience gained studying the magnetic environment around the ISS informs the design of spacecraft destined for the Moon, Mars, and asteroids. Outside Earth's magnetic bubble, radiation levels are much higher. Effective shielding, real-time radiation monitoring, and countermeasures like pharmacological protection are being tested. Technologies trialed on the ISS provide critical data on how to protect astronauts from magnetic and radiation hazards during interplanetary travel. The ISS is thus not only a platform for Earth observation, but a crucible for humanity's future in space. The dance of the ISS within Earth's magnetic field reminds us that even in space, invisible forces govern our journey. Magnetism connects Earth's interior to the surface, the Sun to the planet, and humanity to the cosmos. This magnetic web shapes our environment and conditions the possibilities for life. Contemplating this relationship invites deeper reflection on our interconnectedness with natural forces and the universe itself. As new space stations and habitats are planned, in lunar orbit, on Mars, or deep space, understanding magnetic environments remains paramount. Missions like Artemis and Gateway will operate partially within Earth's magnetosphere or just beyond. Advanced magnetic shielding technologies and space weather forecasting will be critical. The ISS's legacy in studying Earth's magnetic environment provides a foundation for this future. Magnetism, once an invisible mystery, is becoming a vital part of humanity's cosmic journey. The International Space Station moves silently in its orbit, a testament to human ingenuity amid the grand forces of nature. Its journey through Earth's magnetic field is a story of subtle forces shaping survival, science, and exploration. This orbital whisper, the magnetic dance of Earth and station, is an ongoing symphony, one that links us to our planet, our star, and the boundless universe beyond. As humanity steps forward into deeper space, this magnetic relationship will guide, protect, and inspire.